Okay, hello everyone. Welcome back to another session of the RASP seminar. So it's my great pleasure to introduce our today's speaker, Leonard Pappenmeier. He's currently a PhD student at the University of Lund, working together with Luigi Nadi. And yeah, he's going to talk about his latest work on understanding high-dimensional visualization. And with that, thanks a lot for joining us today, Leonard, and please take it from here.
Yeah, right. Yeah, thank you a lot for having me. Yes, so as you said, I'm a PhD student in Lund, final year now. And this is joint work with Matthias Polocek and Luigi Nardi. Um, so, right. So the general topic is black box optimization. And I guess a lot of you are familiar with that, but I'm going to quickly introduce the problem for those who aren't. So black box optimization problems play a role, for instance, in hyperparameter optimization for machine learning or engineering problems. And the general assumption is that you have a function that is expensive to evaluate, and you cannot observe gradients, so you only get these point-wise evaluations. So that limits you to like a few dozen or 100 function evaluations just because the function is so expensive. And one example is hyperparameter optimization of deep neural networks, where you need to train the entire neural network just to get like one estimate of the test loss. Right. So those are the types of problems that we try to tackle with Bayesian optimization. And the way we do that is by modeling the function with a probabilistic surrogate. So here in the example, we have a one-dimensional function for which we have observed 4 points. And if we assume that the observations are noiseless, we know the exact function values at those 4 points. So those are the black crosses. However, we don't know the values in between. But if we make certain assumptions on the structure of the underlying function, for instance, that it has a certain smoothness, we can model the function values at the unseen locations probabilistically. So here we have such a probabilistic model, and the black line is the estimated mean of the function, and the shaded areas are a 95% confidence interval. So the idea of Bayesian optimization is to place a prior over functions. So such a prior is shown on the left. It's like pretty flat. But once you make some observations, you can update your belief, and that gives you the posterior. And we generally call the posterior the surrogate model of F. So that's only one part of Bayesian optimization because, like, so far we don't know how to select points to evaluate. And in order to optimize F, we need to find the optimal point, right? And we do this by iteratively updating the surrogate model and then proposing new points to evaluate. And we find new points to evaluate through an acquisition function that is called alpha here. And the acquisition function trades off exploration and exploitation by choosing points that have both high uncertainty and a low expected value. And in order to select the next point, you of course need to optimize the acquisition function because you want to evaluate the point where the acquisition function has the highest value. And although that seems like you replace one optimization problem with another, the acquisition function is usually much faster to evaluate than the black box function. It provides gradient information, and you can use efficient Newton methods, for instance, to maximize it. And once you run out of budget, you then either return the best observation or the point of minimum posterior mean, depending on how risk averse you are. So the surrogate models that we focus on in this talk are Gaussian processes, and those are basically just very high-dimensional multivariate normal distributions for which you calculate the covariance matrix with a special kernel function and the mean with a special mean function. And yeah, as written here, Gaussian process is really just a collection of random variables, any finite number of which have a joint Gaussian distribution. So although we say it's a distribution of a function, that's only true in the limit, because in practice we can only evaluate it at finitely many points. And then to plot the surrogate model, we just plot the mean and the variance for each of those points. So this is the prior I've shown before. And the prior is just the GP before conditioning on any data. So it's just flat in the beginning because unless we have any specific knowledge about f, we usually just use a zero mean prior or a constant mean prior because yeah, you usually standardize the data anyway. So and if you don't have a good idea about the mean, you can just set it to zero, and then this is what you get. But once you make some observations, you can you can condition this multivariate normal distribution just using the standard conditioning rules for multivariate Gaussians. So here we assume that X OBS and Y OBS contain the locations and function values of the 4 observations we made here. And X is the set of points at which we want to evaluate. By the way, this entire expression here assumes noiseless observations. Otherwise, you would add some diagonal term to one of these matrices. But we keep it, we skip that for brevity. Right, I said before that, so this covariance matrix is calculated by a kernel function, and those really are the meat of Bayesian optimization. That's the most crucial part, I would say. And the examples I've shown before, the Gaussian processes, were created using an RBF kernel, which is the one that is shown here. And the RBF kernel assumes that points that lie close by have similar function values. So the kernel gives a value of 1 if x and x prime lie close together, and a value of 0 if they are very distant. But how distant they need to be, to get a certain value of the kernel, depends on the length scale L, which is highlighted in green here. So I've shown 2 equations here. In the first one, you only have one value L, so that is called an isotropic model. In the lower equation, you have 1 L per dimension, and those are called ARD models. ARD is for automated relevance determination. So here the length scale can vary per dimension. And L is just a hyperparameter of the model that we fit using the data. Right, so just briefly, what's the difference between short and long length scales? Well, if you have short length scales, f varies very quickly. That's shown on the left here, where you have a length scale of 0.05. If you have a long length scale, then f varies more slowly, which is shown on the right. So as I said before, this GP usually comes with some hyperparameters. One of them is the length scale. You usually also have the likelihood noise, and sometimes the function variance. That's also called output scale in BOTORCH. We summarize those hyperparameters here with theta, and we fit those using the data that we observed. And we discuss 3 main approaches for fitting the hyperparameters. So the 3 approaches are maximum likelihood estimation, or MLE, maximum a posteriori, or MAP, and the fully Bayesian approach, sometimes also called model averaging. The main difference between MLE and MAP is that MAP specifies a prior, whereas MLE doesn't. Right, and so you have this prior distribution for the hyperparameters, and once you observe data, you can apply Bayes' theorem to obtain the posterior distribution of the hyperparameters. And what MAP does then is to choose the mode of that posterior distribution in order to set the hyperparameter. So it's a point estimate. It chooses the mode of the posterior distribution to set the to configure the GP basically. The fully Bayesian approach samples from this posterior distribution like a couple of times, and then averages those models. That's why it's called model averaging. We don't talk about the last approach, but focus on the first 2 approaches, which are also a bit more common because the fully Bayesian approach is relatively expensive because it involves this Monte Carlo step. Right, so we fit the GPs by maximizing the marginal likelihood. Or in practice, you usually take the log of the entire thing, and then it's the marginal log likelihood. Here we actually show the noisy case. So here you also model the function noise. The marginal log likelihood has these two terms, the data fit term and the complexity penalty. The data fit term prefers models with short length scales because those make it easier to fit the GP to the data. The complexity penalty penalizes models with short length scales because those are more complex. So there's a trade-off here. And with MLE, you just choose the hyperparameter that maximizes this marginal log likelihood. The hyperparameters of the GP, so one of them is this sigma n, which is the noise variance. The other hyperparameters, like the length scales, are hidden in the kernel matrix here, so they are not shown explicitly, but they are there. An alternative to maximum likelihood estimation is MAP, which is basically like in log space, it's the sum of the marginal log likelihood plus the hyperparameter prior P of theta here. So you just add this log prior term to the marginal log likelihood. And you can use this if you have some prior knowledge about reasonable hyperparameter configurations. And as I said before, MAP then chooses the hyperparameter configuration that maximizes this expression here, which is sometimes called the unnormalized log posterior. Right. So how do these two behave? So in this figure, we show what length scales MAP learns with different observations. So in this case, the problem is a realization drawn from an isotropic 1000-dimensional GP with a certain length scale, 0.5. And we have these blue and orange lines. So the blue line is the MAP estimate if you only have one observation. And the orange line is the MAP estimate with 10 observations. On the x-axis, you have the gradient updates. And then on the y-axis, the length scale that like the MAP estimation converges to one of them. So what you see is that with only one observation, the MAP estimate converges to the prior mode, which is up here. Just for some length scale prior, it doesn't really matter that much. When you have more observations, it converges to some value in between the prior mode and the true length scale, which is at 0.5 down here. We also see that MLE doesn't really do anything at all, and we will see in a bit why that is. First of all, I quickly want to say why high-dimensional Bayesian optimization is challenging. Maybe this is obvious. I'm just going to say it anyway. So it's the curse of dimensionality. So if you have a binary problem, so say you have a binary problem that has a certain amount of parameters, and the x-axis shows the number of parameters, then you have like exponentially many more configurations that you need to or that you can explore. So to model this function accurately, you need exponentially many more data points because, like, just to cover the space, you need exponentially many more points. And the same applies to continuous problems. There, you just need exponentially many more data points to model a function with the same level of accuracy. So say you achieve some good model fit in 1 dimension, then you need exponentially many more points to achieve the same model fit in higher dimensions. Right. So what people have done for high-dimensional Bayesian optimization are making certain assumptions on the structure of the function. So there's this class of additive GPs that assume that F has an additive structure. Then there are the subspace methods on which I've worked myself in the past, where you assume that the model has a low-dimensional effective subspace, and you basically aim to recover that, and then you model the GP in a low-dimensional space, and hopefully this whole low-dimensional space coincides with the true effective subspace. And there are these models that assume axis-aligned subspaces. So SARSPO, which also was featured in the AutoML series in the past, basically aims to automatically find the active dimensions, assuming that the problem is axis aligned. That means that some of the parameters have no effect on the function value. However, we saw 2 papers in the past that said that vanilla BO just works out of the box in high dimensions. And this talk really is about why is that and why didn't it work in the past. So, right. So let's start with talking about why high-dimensional BO didn't work in the past. So this figure shows the maximum gradient norm of the marginal log likelihood during the first 50 iterations when fitting a GP. So we fit a GP using gradient-based optimization, and we look at the maximum norm within those first 50 iterations. The x-axis here shows the dimensionality of the problem, and the y-axis shows the initial length scale with which we configure the GP, right? So starting from some initial length scale, we just run the maximum likelihood optimization then. So yellow in this plot means that the MLL changes a lot because the gradient norm is high. And in the figure, each combination of initial length scale and dimension, this black line shows the point at which the maximum gradient norm falls below the machine epsilon. And we use the machine epsilon as a proxy for vanishing gradients because it's there's no like agreed upon definition of vanishing gradients, but machine epsilon, I think, is a pretty safe estimate. The dashed red line here shows the initial length scale value used in earlier blowtorch versions. So up to version 12, blowtorch used a fixed length scale initialization strategy that set it basically to natural logarithm of 2, and that's what this dashed red line shows here. And what you see is that this default initialization strategy led to vanishing gradients for problems with roughly more than 300 dimensions. So we have seen problems with more than 300 dimensions in the high-dimensional BO literature in the past. So for instance, the SVM benchmark that was used in the SASBO paper by David Erickson et al., or the Lasso-Hart benchmark that I used in the past, those have more than 300 dimensions. So the SVM has 388, the Lasso-Hart even has 1,000 dimensions. So this vanishing gradient problem is an issue on the recent benchmarks. However, it can be solved just by scaling the initial length scale by square root of d, because that accounts for the increasing distance in more high-dimensional spaces. So our first suggestion to make high-dimensional BO work is to change the length scale initialization. Right. So we have identified this problem of vanishing gradients of the marginal log likelihood. Next, we look at the acquisition function. And here we show that the acquisition function can also exhibit vanishing gradients. And we also see how we can avoid these vanishing gradients. So the figure is kind of similar to what we've seen before. So on the x-axis, we again have different dimensions. On the y-axis, we have different length scales. However, in this figure, we create a GP sample with that configuration. So, for example, 25 dimensions in the length scale of 0.1. And we condition a GP with the same configuration on 20 random observations. So we don't fit the GP, we just set it to the correct value. So our problem is a draw from a GP prior with that configuration. And our model that we fit, like we know the underlying hyperparameter configuration, we just set it to the correct value. So there's no model mismatch between the problem and the GP. We then optimize the acquisition function, and we do this by first drawing 512 points from a scrambled snowball sequence. So globally, we evaluate the acquisition function on those 512 points. Out of those, we choose the 5 best points as starting points for the gradient-based optimizer, and we run the acquisition function optimization until convergence. And what this figure shows is the average distance between the starting points and the endpoints of the gradient-based optimization. What we see here are these gray areas, and those are the areas where there's zero distance, like exactly zero distance between the starting and the endpoints. And those are the areas where you have vanishing gradients of the acquisition function. Because if the gradients are zero, then You don't update there's no distance between starting and end points. And we see here that vanishing gradients of the acquisition function occur relatively early. So if you have a problem that has a length scale of 0.1 in 50 dimensions, and you manage to correctly fit the model to the correct hyperparameter configuration, then your acquisition function will exhibit vanishing gradients. So a lot of methods will suffer from this. So let's see how we can fix this. Here, the left figure is basically the same figure as before, but we changed the way we optimize the acquisition function. So before we drew 512 random points from a scrambled snowball sequence globally, but now we also add local samples. We call those RASP samples. RASP is random access-aligned subspace perturbations. And those samples are drawn close to points that have performed well in the past. So we call those local samples because they are close to other points that we already observed. So overall, we then have 1024 random samples. And out of those, we then again choose 5 starting points for the acquisition function maximizer. And for each combination, so the right figure for each combination and length scale shows the fraction of points that originate from these local samples. So if you have a yellow point here, that means that a high fraction of points come from these local samples. If you have a more purple point, that means that a lower fraction comes from these local samples. And so we observed 2 things in this figure. First of all, there's no gray area here. That means that all points now travel a positive distance, so there are no vanishing gradients. And for short length scales and high dimensions, an increasing fraction of the points stem from the local samples. And since we know that the acquisition function surface is widely flat for low length scales and high dimensions, this indicates that we actually operate quite locally, because we know that the acquisition function has these vanishing gradients somewhere. We just don't run into them now because we start from the local samples. So our next recommendation is to use RASP to avoid vanishing gradients of the acquisition function. And this is particularly relevant when you use MLE instead of MAP, since MLE is unbiased and can more easily converge to short length scales if your problem actually requires those short length scales. So we provide some further evidence that RASP makes high-dimensional BO work. For this, we first need to introduce the notion of OTSD. OTSD stands for Observation Traveling Salesman Distance. And it is the approximately shortest route connecting all the points that were selected during the BO loop. So it's just the traveling salesman problem basically here, but we use some approximation of it. So this right figure with the 2 panels shows the OTSD for BO loops with local sampling in the left panel and without local sampling in the right panel. And high OTSD values indicate high exploration, low OTSD values indicate little exploration. We optimize here the acquisition function for GPs of different length scales. So we set them again to the correct hyperparameter configuration. And those are the blue, orange, and green lines. And the black line shows the OTSD for randomly sampled points. That one is usually quite high because randomly sampled points are spread out in the space. So this is kind of an upper bound for the OTSD for us. The first 10 iterations of the BO loop are the DOE phase, in which we just initialize the model on randomly sampled points. And that's why for these first 10 iterations, the OTSD of random sampling and BO overlap. But after that, BO starts and then they start to differ. And what we observe here is that without local sampling and for short length scales, BO is almost as explorative as random search. So we see this in the right panel for the blue and orange line. And only for longer length scales, BO starts to show a different behavior. So this is the green line. And what we hypothesize here is that this is the point where the acquisition function exhibits non-vanishing gradients. However, when we do RASP sampling, as we see in the left panel of this right figure, none of the configurations behave like random search. And here the acquisition function should be maximum close to good observations. And therefore, we would not expect Bayesian optimization to behave like random search for local length scales. Instead, it should be quite local. Therefore, we argue blue and orange in the right figure suffer from vanishing gradients. And RASP fixes that, and that is why we don't see this random search-like behavior in the left panel. So after all these discussions, we can then derive some conclusions. First of all, maximum likelihood estimation, if properly initialized, does not exhibit vanishing gradients, and it is unbiased. MAP also does not exhibit vanishing gradients because its log normal prior term always gives shape to the maximum likelihood. However, it is biased towards the prior mode, and that is usually not desirable unless you have specific knowledge about reasonable hyperparameter configurations. Therefore, we argue that high-dimensional BO should use MLE with a scaled initialization, with RASP sampling to avoid vanishing gradients of the acquisition function, and with a scaled initialization to avoid vanishing maximum likelihood estimation, to avoid vanishing gradients of the marginal log likelihood. And we combine these components into an algorithm which we then call RASP. And we have some experimental results here. And we show that this simple approach is competitive with the state of the art. So we compare our approach, MSR in red, with the dimensionality scaled priors, which were proposed in the Vanilla BO paper by Karl Bafner. ZASPO, proposed by David Erickson et al. In the purple line, and Bounds, proposed by myself in the orange line, as well as MLE, where we just scale the initial length scale, that's green, and MLE in the traditional setup where we don't scale the initial length scale, that is brown. The benchmarks that we look at here are the MOPTA 8 problem, that's a 124-dimensional vehicle optimization benchmark. Lasso DNA, that's a microbiology classification problem, and two Mujoko benchmarks, Ant and Humanoid. Those are very high-dimensional and quite noisy. And what we see here is that MSR is competitive with the blue line DSP on all benchmarks. Even the green line, where we just scale the initial length scale and then run regular MLE, is really competitive. So we don't see vanishing gradients here since the models learn length scales. We don't see vanishing acquisition function gradients here because the models learn long length scales. So I said earlier that if your model has very short length scales, then you have these acquisition function vanishing gradients. We don't have that here because like all of these length scales are quite long. You can see that in the paper. But this is not always the case. I mean, it's the case for these benchmarks, but if you have a problem that truly has these short length scales, then you would also run into acquisition function vanishing gradients, and that is when you need RASP as well. So we generally recommend adding RASP because we have never seen it to perform worse than not including it. It also performs as good as the green line or even slightly better here. So it's just good to add. What we also see here is that the old MLE just doesn't work, and that is one of the reasons we think why high-dimensional BO didn't work in the past. So really these vanishing gradients of the marginal log likelihood on these very high-dimensional problems become an issue here. So in summary, maximum likelihood estimation is enough for high-dimensional Bayesian optimization, but scaling the initial values is crucial. MAP, which was proposed, also works, but has this bias towards a specific length scale value. And for problems that require short length scales, a local strategy like RASP might be the only resort. So that was it.